board. And so this is our code. So feel free to go to lab 5 and rip it off. And we are going to key it in and play with it. Okay. So I don't care. Let's create a new directory here. We'll call it. No, this is actually lab 6, isn't it?
Yeah.
So I make dir lab 6. And we'll just call it main.c for the sake of argument. And we're going to paste it in. Okay. So what we will do here is we will go through and explain what all of this is and how it relates to you. Okay. And then we'll modify it to where we put in a number and then some number gets added to it automatically and it prints it out. Okay. So that's where we're headed. So by the time we're done, you're going to have a stub that's going to help you with lab 6. Okay. And then in lab 6 with the argv, argc, we'll revisit it in lab 8. What we'll be doing in lab 7 is a kind of a reiteration of everything we've done. I'm giving you 2 new working pieces of code that you're going to turn into functions that you will add to your ever increasing library. Okay. So that's kind of where we're going. So we're still learning how to put the pieces together. Okay. So this compile line will be pretty start with. Now, being lazy, you can do gcc main.c and just hit enter. And then if it compiles cleanly, you're going to get an A.out. So what's the answer when you run a compile with no output?
A.out.
I don't know if you've seen this book or not. But did I show this book earlier? I can't remember if I did. But it's actually really good. But you will not find assembler in here. You're going to find Java and C and C++ and C, but you're not going to find assembler. Okay. All right. So now I'll run A.out, see what I come up with. And it says, okay, hitting enter, the number is null because I did not put in any parameters today. Now let's add a parameter, add another one. Notice what it did. Things that were within the code was stored. What it did is save the quotes. No. So when we go to parse this, what are we going to have to do with the spaces? Those are the legitimate characters in this string. Okay. So when we can say hi there, we can say hi there. And it gave me no errors. It just took whatever I put on the command line and printed it out. So let's keep adding a bunch of stuff to it. Let's see how far out it goes. So it keeps going. Does it end somewhere? Yeah, I think it ends somewhere around 23,000. It's the size of an integer. So it can go pretty big for a command line argument, which is, makes it hard to parse. This is another thing to consider is that we have a shell that we use. The shell, which we currently have on our box here, bash. Bash still has argvs and argcs, which are only allowed 9. Okay. And I don't know if I have anything in here for that. Let's see here. IPs shift test. I might have it in another account. Hold on a sec. Let me bounce over to my other accounts here. And where did I put it? Here. Here we go. Shift test. This is bash. This bash is all written in C. So some of the weird, quirky behaviors you see in C are inherited in bash. And some of the weird quirkiness that you see just in syntax in general comes from the old days of having limits on how much you could store into things. Okay. So if I take this shift test and do the same thing, all right, it's giving us a dollar, a dollar @ dollars hash, dollar star, question mark. Does that ring a bell? Dollar question mark. Give me my return code so I could see what my code was doing. And so let's go ahead and run this. And I'll give it a bunch of characters. Oops. So what it's showing you is those different, the dollar, this is the process ID that gets tied to the kernel. This is all of them. This is argv, argc, and C, right? It prints all of them. And we went through a for loop to print each one. So how does this relate to you? Well, on the command line, this same property works in Windows. Syntax is different, but the same idea that you get a limit to how much you can put into your shell script comes back, okay? And then how many total? 12. And then again, this is another way to count them. There's the name of the program. And then there they all are. Now, if I continue this, what happened is in this shift bash will only allow for 9 arguments. What happens if you've got 10, 11, and 12 on your command line? Bash has this thing called shift. You process the 9, you shift, and then you can get to 10, 11, and 12. And where is that held? That's held in the C program in our argv, argc stuff. So when we say, give me every argument, that's the argc, and give me all the characters that are in the pointer to arg vector. So it's pointing it all out. Now, if we were to look at this code and say, hey, I want to add I'm going to enter 2, 3, and then I hit enter. And I want it to display an add for 2 plus 3. Where and how would I do that? Now, remember, we can cheat. This is all practice code. So it doesn't really matter what we do. We're just kind of having some fun with it. Okay. But what happened here? What's this actually printing here? It's taking argc, or all of them, and then giving me each individual index in the vector, starting with 0 and 1. So 0 is always the name of the program running. 1 is the first parameter, and 2 is next parameter. So we want to add argv argc. Let's take a few minutes and fiddle on the code and see if you can get 2 digits to add from the command line. You can do it as simple and sloppy as you want. I recommend doing something really simple, like use a printf in there somewhere. Okay. You know, I stress argv and argc a lot. The reason being is that understanding how it works and what the limits are can save you tremendous amount of headache. I mean that literally. A tremendous amount of headache can be saved. if you work on it a little bit, rather than waiting for me to give you the answer, your brain's gonna work better. And you'll be able to start troubleshooting and doing the magic there. That's where the big bucks happen. What a mess. At least that cleans it up a little bit. Not really. Anybody have any luck? Anybody having fun pondering this? Everybody going, why is this so hard? Well, yeah, it's the quirkiness of C. This is, I was reading somewhere that the people that are jumping into Go come from scripting languages background, not hardcore system tooling. And that makes sense because if you spend 10 years learning C and C++, you're not going to want to abandon ship. Okay. So here's something that sort of doesn't quite work, but I will explain it here in a second. Let me show you what it does first. Okay. So there it is. I copied it and renamed it to play. And I'm just doing the GCC a dot out. And I'm giving it 2 or 3 different ones. So I'm adding 2 and 3, and it gives me 5, and it gives me exec name and 5. That's actually the total. So if I run this again and say, you can see it gives me the right total. But look how this is. This is the name. This is where the total is. So why does it print the total like it does? Well, I have a N here, right? I probably need another one. Let's throw another one in there just for grins and giggles. That should clean it up a little bit. Yeah, a little better. Notice I can add characters and it doesn't do anything. It doesn't change my answer, but it doesn't break. But when I add less characters, ow, this is part of what you'll need for the conclusion of lab 6. You got to put a test in there to say, hey, you don't have enough count. What do we got to do? Okay. And notice I added the library. That gets sneaky because where that's needed is right here. Going back to ancient history through the scroll here, it took whatever we put on the screen, 1, 2, hello there, quotes, and throw it and printed it. It didn't do anything on it. Okay. Believe it or not, that's called ASCII. And this subroutine or method or object or function, whatever you call it, is ASCII to integer. Now, this is a relatively old school way of converting your command line argument into something usable. There is also ASCII to string, which may or may not work with our hello that we did, and we passed hello first name and said, remember that? We put in our first name and it said hello first name, and the hello was a function that was up in the header. Yeah, that goes back a couple weeks, maybe a week or so. It kind of leaks out between classes. I get it. All right. So that's a little cleaner. So now I can say, here I can say the totals are . The sum is. How's that? Let's see how that looks when we're done. But does it does it still die? Bummer. Why does it do that? Well, lots of reasons. We are sending something, we're asking for it, and we're not explicitly testing. And this is where I like to get on my soapbox. I said, data got to be clean on the way in, it's got to be clean on the way out. And I get off my soapbox. I don't care if you're putting data in or pulling data from a system. You should always do a sanity check on the data flows because you don't know what you're getting. And if you don't know what you're getting and you're shoving it into the database, you may have hosed your database. And restore from your previous backup is not going to work when payroll checks are just about ready to be printed and you corrupted the entire database. So data validation in and out. People will tell you, well, if it's clean going in, it's going to be clean coming out. I said, nope. If the user touches the data, there's a chance it's going to get screwed up. Guaranteed it will be. Okay. So that's just hard-won experience there. So let's clean this up a little bit now that we kind of know what we need, and we just want to add those two numbers. Okay. So we want basically taking the first and second argument list and adding them together. Okay. Since I don't have my for loop anymore, I don't need that. So let's clean this up a bit. Now there is some shortcut. That's supposed to work, but it doesn't seem to work with the default flags. So we'll experiment that in a second here. And see what happens. Well, not quite printing correctly, but it is getting the right sum, right? Now, what I need to do then is do this. Ta-da! Now it's looking cleaner. Now, how do we check for things? We want to be able to check for how many argument counts. I want 2 argument count, right? Where you don't want 3 arguments, we don't want 1 argument, because we don't want seg faults. And we're doing this on a very simple basis here. Let's see here. How would we do that? Well, let's look at the original code. This is now called play.c. And the original code was called main.c. And you can kind of see why I like to put the name inside the code? Because it just makes, I'm going between screens and I have two open editor sessions. Where am I? I just got lost. Well, if you put your name of the file in the same place, line 2, you kind of know what you're working on. So where do we keep the number of arguments as an integer?
RB.
Bingo. So we need to say if argc not equal to whatever, then either return or continue. And we can do this multiple ways. And I have a challenge for you. Now, tonight, we will use if. Okay. We'll just use an if. I do need to bring this up because it is an area of very interesting, if useless, consternation. I want you to imagine all the programming you've ever done and remove all ifs. How do you check things? You have to completely change your mindset to use a completely different model of programming. And yes, it's out there, and it's called functional programming. You can write functional programming with no if statements. The tool has to support it. True object-oriented, there's two classes of object. I'm going to go off on a little rant here. Object-oriented notation, there's two camps. There's the one you're familiar with C++, which is objects just bolted on top of C, basically. And then there is the Smalltalk model. And the way this works, this is also where Ruby comes in. But Ruby put in an if statement, and they call it syntactic sugar. So programmers kind of know that they can make it work. An if works like an if, like you expect it to. But do you need it? No. If Ruby didn't have an if, do you think people would use it? No, because our brains are stuck on if. That's just the way we think. Smalltalk uses this concept of message passing. So if I want to do something with these two objects, there's a message that goes between the objects. Then things happen. So message passing was all the rage there for a little while, but it's really nothing new. They're using this in very scalable types of things in asynchronous communication. Does that sound familiar? Hey, are you there? Yeah, I'm here. That's async. Okay. Synchronous is just sending it off and you're just expecting the person to pick it up. Okay. That's synchronous. Then that's based on clocks. Okay. So little side rant there. That everything you learn about programming, there is a fun book to read, 7 Programming Languages in 7 Weeks.
Is it possible to do a real simple example of what a not using an if statement would look like?
I actually don't have anything simple to show you.
Okay.
But I do have a video where Sandy Metz talks about it. And she goes through the entire process of taking a program that uses ifs and converts it into using the truthiness idea. Where is it true or false? And then it just iterates over it. And she uses Ruby as the example. I like to attribute this lecture to a philosophical discussion with real world benefits, because oftentimes we throw in an if because it's quick, easy, and fast, and terribly inefficient. So it depends on what you're working on when you're working on it. For example, V'ger 7 or whatever it is, way out there on the outside of our galaxy, they just sent some code to it so it doesn't build up cruft as it's flying through whatever it is it's flying through. This is technology from the 70s. And it's still out there working. NASA has a very different view of programming than minimal viable product. Let's ship it. Let's take Windows NT and let the customer figure out all the problems, and we'll collect the error logs, and then we'll make it better and sell them another release. Well, you've got $10 billion of cash flying out there. Mistakes cannot happen. How do you write code with that kind of rigor? It's a completely different mindset than what you learn in school. Okay. We learn in school, oh, yeah, it worked. And that's about it. Okay. So let's.
Sorry, what was that functional Ruby lecture called?
Oh, I'll post it on our lab.
Okay.
The Sandy Metz. I do it in my 271 class because it's very engaging. And I'll put out the slides for the two camps of object-oriented. And there's different models of programming. Used to be all or nothing. But the languages that have evolved in the last 10 years are very pragmatic. If you want to write functional, you can write functional code in Python or Rust or Go. If you want to write objects, you can do it in Python. You can't do it in Go. Go was never designed to do object. Java, that's all object or procedural. Okay. But it's I encourage you, if you want to become a better programmer, is to keep investigating other languages and their design ideas, because you will find that there are patterns that keep coming to the surface and the good ideas float to the top, and they just keep floating to the top, decade after decade after decade. Zig, new programming language, hey! Well, all the great ideas, they just encapsulated into one programming language. How are we going to fix this? The problem is this is only somewhat accurate. Because I could say, hello world, and it's going to try to add to strings because we're not explicitly checking for strings. That's not the point of what the exercise is. The exercise is learning argv and argc, because that shows up in all of your programming languages. Okay. And then return one error code. Okay. And then this gives us, this fixes our problem with this. Although my error code is wrong, it should say integers. Gives me the same error, and it gives me the right answer. So what did I give you? Basically, the answer to lab 6. Okay. But then again, you'll see it in lab 8, I believe. So this did work. Okay. Now, integer. Let's use a better command line here. Call it play. And wall. Give it some debug symbols. And let's just do it that way. Sure it all behaves. Yep. Here's my answer. Looking good. All right. Now, what we are doing is, if you remember this and you write down this code somewhere and you keep it, you will use it again and again and again, no matter what programming language you choose. Okay. That I can guarantee you. Now that we have this, let's look at it in assembler. Okay, so we know we don't need the first one. That's just explaining things, global. And then these are specifics for the C. We'll get into more of this. Wonder what the PLT does. Now we'll be using this same compile line to generate the assembler pretty much the rest of the class. Okay, so just highlight that and throw it into one of your notepad files that you're keeping notes on, or put it in your history file, because we'll be using the MASM for the duration. It is a little easier to read. It's just as hard to understand. Okay. Now, the next thing I would like to approach is we will write 2 loops in C. And our 2 loops are simply going to be a while and a for. It's very simple. And we're going to compare the assembler. And then this is where we will begin our journey of learning more about registers and moving data in and out of registers. And if we want to see what is really going on with our compile line, we use this -v for verbose. So this is collect. The verbose option shows you what libraries are being brought in when you use the command called that's underneath covers of GCC. It calls something called collect to, and then collects all the libraries and then links them. Okay. There's the options. There's a lot of libraries again included. This is why we use GCC to link. So here's the assembler, but it still used GCC to link it. Okay. Did I explicitly tell it to generate assembler code in this line? There's no dash S, is there? Did it generate assembler code anyway?
Yeah.
Yeah. Okay. That's a lot of stuff. So when you play around with Linux and you install stuff, when you install a base Debian, it's maybe 1,000 packages. And then as soon as you as a desktop, it goes up to like 20,000 packages because of all libraries it needs to talk to the multi-level, multi-library talking to library. Okay. So this next foray, this is very simple. What we're doing here is we're taking a hello world using a what they call a uni standard, as in Unicode standard, and we're defining null just to make it explicit. Okay, as x00. Now, what that means is, let me see if I can actually show you. You know, I really should create a demo page that does this. Give me 2 seconds. I'll do that. Let me see if it works.
Yes.
Oh, that's right. Can't do it that way. That's not going to let me cheat. Best laid plans of mice and men. Okay. I'll just have to explain it. When we are surfing the web, you will come across something and you will see this %20 in your URL. That is an ASCII hexadecimal space. The reason we're using null here is when they designed C and the very first iteration of Unix that they built it on, they terminated a string with a null terminated string. Rather than a carriage return or a line feed, C strings is what it is called. And when you take 271, you may have had a little blip about C strings. They're null terminated strings. Does this get into any headaches down the road? Maybe. If you move into databases, what's the difference between null and no data? It is a database specific implementation. So 20 is actually a space, not a 0, 0. So when we take this string here, we're saying take this string and as long as it's not equal to null, go ahead and write it out 1 at a time. So this is very simple. It's just taking the string and it 4-string printer, semicolon, string printer is not equal to null. This is the test. And then increment the printer or the string pointer, excuse me. So what it's doing is it's saying what's in the string and print the first index, second index, third index, fourth index, until you hit the null and then stop. That's all it's doing. Okay. So take a few minutes, type this in, and we're going to do this twice. Once for a for and once for a while. And then we're going to compare the assembler. So Just as I thought, there is actually a anti-if campaign. So you can actually go look up what it is. And part of it is tongue in cheek. But part of it is actual legitimate, is oftentimes your code grows unruly and very gnarly because you don't sit down and take the time to refactor it. Sometimes you have to actually sit down and rewrite it, and then you can solve a lot of problems. And then on the other screen, I will bring up the other one. It has the same syntax coloring. You can see it pretty much exactly the same, except that while the condition is a little shorter. Now on a piece of paper, blank, write a for loop in your favorite language. How many remember the question of any for loop can be written into a while loop, or is it any while loop can be written to a for loop? Which statement is true? Not meant to be a trick question, but it kind of can be. It shows up in cracking a coding interview. Any for loop can be rewritten as a while loop, but not all while loops can be written as a for loop. Because a while loop gives you the option of one or more exits. A for loop gives you an option of one. That's a textbook answer. You can argue anything any way you want, but I like for loops because you know when they're done. And in some programming languages, they are orders of magnitude faster than a while loop. So it depends on the language you're working in. For what we're doing, doesn't matter. Now, when we write assembler, we'll be using AS to assemble it, but we're going to be using GCC to link it. So we don't have to worry about running it through collect2 to collect 39 libraries all at the same time. We'll use the tool so we can kind of learn our assembler language without having to spend 3 weeks learning a tool chain. Everybody got it keyed in? Once you get him keyed in, use the wonderful long gnarly thing here. Hello world for.c. Let me close this file and do the same thing for the hello world while. And now I have two new S files, for and while. For grins and giggles, I'm using diff S. Oh, look, there's only one line different. Let me bring one up here. So basically, even though syntactically, the while and for are very different, according to C, but at the assembler level, they're basically identical, except for the name of the file. That's what diff is saying. And since we know in these, we can say, I don't need the last four or that very first one. So let's edit the for. Do the same thing. Run diff again. There is no difference between a for loop and a while loop in assembler. So in C, who knows? And then next week we'll pick up with this and add the do until equivalent, or do while, I think it's called in C. That one's a little different because the logic says you will always go through the loop at least once. The for loop can be a condition where it says, whoop, we're not even going to go once, and the same with a while loop. Okay. But now let's look at the assembler piece. And this is kind of where we will pick up on Thursday, tinkering with this. Okay. What if you wanted to create a program in assembler that displays something other than hello world, and it says, hello, your first name? What do we need to change? Taking the easy road. Well, hello world, right? And this is the, forget which one this is. Change word, scale. This is the S. So I will say A, S, hello world 4S, output H4.O, GCC, HO, output, and let it do its magic. Wow, I just wrote some assembler code. Awesome. What did I do? Not a whole lot. I changed one word. And then let's do it this way. That was the for loop. Okay. I changed one word. And what did I do? I ran the assembler and created a .o. My relocatable object, but it is not executable. That's what that line does. And then I compiled it using the standard compile line. Except I said GCC H4O -O H4, which turns it into my executable binary with all the lovely overhead that comes in by magic from the linker that's part of GCC. So it basically runs collect2, and then it runs LD all magically underneath the covers. So we kind of wrote our first assembler program, right? Sort of. Cheated? Yes, that's quite all right. And we will go through and explain what all that other stuff means as we move along. Okay. So let me bring the code up so you guys can look at it. Oh, did everybody get the C codes written? There's the C. And then the while. As you can see, they look very similar. So I encourage you to work with this. Remember our program that we just did before this one? Call it Lab 6. Remember this? Ancient history of an hour ago. How would we take this, convert it to assembler, take that number and pass it to hello world, the one we just did? That's where you're going. Okay. That's the kind of thing we'll be doing as we kind of trip and stumble and stub our toes down the road to learning this stuff. Think I put this in S already. I did. So this is what it looks like in here. So where does it call the second? Notice there's a call, a print. Here's the usage, the errors. So somewhere in here is my argument, second argument, and third argument. So it gets added together. Play with this, tinker with it, think about it. Because this is what we'll be doing as we go forth. Okay. Brainful. Here's ATOI. Here's one. Here's the other one. Are you kind of getting the idea of what's going on here? I've got a double word printer, this register called RBP, tracks keyword, and then ATOI. It's going to be our X or Y. Here's our X or Y. Notice we're using RAXs and RDI and EDXs and EXs. And then we print F, the result, somewhere down in here. That makes total sense, doesn't it? That's okay. It will. In time, maybe. I don't know. We'll see. See how deep we want to go into this. So that's what we wanted to do today, is I give you two legitimate pieces of code that are obviously different, but yet in assembler, they are identical. And you can do timings. Now, this is really hard to do on the machine we've got, but let's see here. I don't think I have too much on this one. I do know where I have it. Let me do this. I'll just pop onto another box here. Okay. This is something I've been slowly accumulating over the years. All this does is print out 1,000,000 stars per program. And I've got it in Go, Fortran, C, C++, Rust, Z shell. And I'm using this time command, and I'll show you how that works. Is it when you run a command, say like you want to run your hello world, on Linux, you type in the word time, name of your program, it runs your program, exits, and tells you how long it took to run that program. Okay. Is this very accurate? No. But it gives you a ballpark figure of what is grossly slow versus what is not so slow. Okay. So I'm going to run this. So the very first one is bash, I believe. So bash takes 5 seconds to print 1,000,000 stars to the screen. And that means both user and system. In other words, how long is the user waiting in their slice versus how much is it using its system, the kernel usage. So based on how your code is running, so 5 seconds, and then it's using a simple read statement to stop. And then it goes on to the next one, prints another 1,000,000. This is dash, which is another programming shell. POSIX compliant. It doesn't do a lot of what bash does. There's no arrays, no exec. Pretty primitive, but as you can see, it's twice as fast. And then we have Fortran, 2 seconds. Then we have Go, which is 1.8 seconds. Now, Go has 2 ways to run. You can run Go interpreted or compiled. PHP, that's not too bad. Julia, anybody heard of that one? Big time data science programming language. It's what non-programmers are using to crunch numbers, i.e. all those people that want to collect your data and your mouse click habits and find out what to sell you. Julia. Ruby. Python 3. Did you see how fast that was? 0.3 seconds. They have done a lot of work between Python 9 and Python 11 to make Python screaming fast. Is it going to get there? No, but it's significantly faster than it was. Okay. Look how fast Lua was. 0.1 second. Why is that? Lua is basically a wrapper around C. And Lua has a compiler too. And the compiler, the Lua C compiler actually converts to C, calls the C compiler, and makes it even faster. Okay. So Lua is a really cool language if you've got a big system and you want to add scripting to it. Games, that's where they use it. Perl, 0.09. Perl is really, really fast. They spent years optimizing it, and Perl is very obtuse. It's called write once because you'll never remember how you wrote it the second time. You got to be in it every day to stay sharp on Perl. I know, I was there. Rust seems slow, but remember what Rust has a ton of overhead. I'll show you what I'm talking about. C++ is 0.06. That's pretty quick. D, finance, near real-time trading, quants. Hey, I need to be able to get an arbitrage on this 5 millisecond lead so I can make money within this 5 milliseconds. That's where they're using D. C, 0.48. And then that's it. So each language has its strengths and its weaknesses. And so you can use the time command to find out how long it takes to run something. So let's do exit here. And let's see how long it takes to run that play. Time, play. So it shows you how long it takes. /play. There we go. Oops, would help if I've been. Did I compile it? Ooh. Lab 6. That would help. So it shows you how long it takes to run that. Not very long. Okay. We covered what today? argv, argc, in C. And we looked at it in assembler, but we didn't do much. We took a for loop and a while loop, got it to work in C, converted it to assembler, and saw there's basically no difference. So what is really going on? That's where we'll pick up on Thursday. We'll do some more with this. We'll add the do while in there, kind of revisit this. Okay. And we'll start learning moving stuff around in the registers. All right. Questions? Complaints? There is another lab posted. It's lab 7. And as a quick overview, I'll show you what that is. So lab 7 is in essence this. Whoops. So we're keep adding to, whoops, I guess I should refresh that. Okay, I'll try that again. 273. Lab 7, and basically your mission is to turn these into functions. So you pass a number to it and it calculates the factorial. You convert this to a function, pass a number to it. Just like you did with the foo and the add me, because main adds a number, right? And then you create some sort of a call that actually calls your routine that you've modified. So this is going to revisit, how do I take working code and turn it into a function that I can call from my main. Notice here. And the fun little thing we get to do here is, can you put multiple H files into one and call it mylibs and put them all in the .h file? Yay, nay, maybe, maybe not. Okay. So we add them, compile. Now, this is a revisit. Convert the fib.c and the fib or fact.c into S file. And relink. Will it work? You all should instantly say, because you've been paying total attention to every word I'm saying, as if it was the last thing you were going to hear. Of course, you're not going to remember. This is why I'm revisiting it, so you can remember. But we're linking this with GCC. So we've learned a few things about the linker in GCC. Okay. All right. And that will be the next lab. I think this is like November 9th or something. So we've got a ways to go. Plenty of time. But since we kind of covered lab 5 and 6 tonight, you might want to go visit those before your brain leaks it all out. Okay. All right. On that note, I'm done yammering. So let me stop recording.